last class, we had turned to discussing theories with 4 supercharges. We decided to discuss chiral fields, that were superfields that obeyed the condition d bar theta 1 is equal to d bar theta 2 on phi is equal to 0. Okay. We discussed that the expansion of the superfield phi was in the following terms. Phi was equal to little phi plus I square root 2, this is Diksha square root 2 psi 1 theta 1 psi 1 plus I square root 2 theta 2 psi 2 plus I theta 1 theta 2 f. And we worked out the Lagrangian for, I believe, we looked at the Lagrangian, we looked at the action d for theta dt phi bar phi with a minus 1/4 plus half integral w of phi d2 theta dt. We worked out this action. In fact, maybe it's a good idea to put it down on the board, so if somebody could help me with that, please. Plus complex conjugate. Thank you. Plus complex conjugate. And Shuman, would you be able to read out the action? So let's see. Phi bar dot phi dot. Minus I psi 1. Okay, so we got this action. Actually, one last request, Shuman. We also found F in terms of the auxiliary field. Help me with that. Okay, F star is minus I W prime of phi, and F presumably was equal to, was it equal to minus I?
No, just I.
Just I.
W prime star prime. Yeah. W star prime.
Okay, thank you. Yeah. Okay. So in this class, we're going to study this model a little bit more in the first part, and then move on to studying, hopefully by the second part, move on to studying theories and moving in many dimensions. Okay. So let's see. So the first thing we want to do is to study how all these fields transform under supersymmetry. These fields, phi 1, psi 1, phi, psi 1, psi 2, and f. Of course, f is auxiliary, but anyway. Okay? So what we want to do is to study how these fields transform under supersymmetry. But of course, we know how they transform under supersymmetry because we know the action of Q on the superfield. So we just have to open that out and get the answer. Okay? So let's do this one more time in full detail. Okay. So remember that Q1 was equal to del by del theta 1 plus I theta 1 bar del by del t. And there were similar expressions for Q2 and Q2 bar. Right? For instance, Q1 bar was equal to del by del theta 1. Was it plus I? Yeah, plus I. Theta 1 bar plus I theta del by del t. And similarly for Q2. Okay? So what we want to do is to take that field, capital Phi, act on it with Q1, isolate the terms that are coefficients of particular theta factors, and from there read off the transformation under supersymmetry. Okay? So though we can do it more slickly, for the first time we'll just do it in the stupidest possible way, just to convince you we're not hiding anything. Okay. So you see that expansion there looks innocuous, but remember that every field in phi was a function of everything was a function of tau, which was t minus I theta 1 bar plus theta 2 bar. So every field in phi, okay, was a function of that, and every field in phi bar was a function of the complex conjugate of this. So the minus sign became a plus sign. Okay, so if we really do an expansion of phi, we really want an expansion of phi in full Taylor series in theta, we have to expand out all the component fields. So let's just once in our lives do it. Okay, so let's do it. Sorry, I should have written here in this list of results, there was also phi bar was equal to phi star plus I square root 2 theta 1 bar psi 1 bar plus I square root 2 theta 2 bar psi 2 bar plus I theta 1 bar theta 2 bar f bar. Bar means complex conjugate, and everything is now a function of tau bar. Right? Thank you. Thank you. There's a factor of 2 in the last thing. That should have been there up as well. Thank you. Okay. So we want to work out the supersymmetry transformation properties of this field. Like I say, there are, there's slightly slicker ways of doing it, using the fact that tau is annihilated by the d operator. So you can use that to simplify the calculation a little bit. Many of the cancellations that we are going to get will become manifest from that point of view. But once I'm going to do it just opening out, just to convince you there's no trickery going on here. Okay, so let's just take that expansion out there and make it an honest Taylor expansion in theta. Okay, so let's do that. So phi is equal to, well, there's little phi. I'm going to work in powers of theta. So this little phi has no expansion here. It's just now in everything I write here, things are functions not of tau but of t. Okay, so there's little phi of t. I won't keep writing of t, but it's always understood. Okay, then there's plus I square root 2 theta 1 psi plus I square root 2 theta 2 psi 1 psi 2. That has not changed because the first correction comes at order 2. Now let's take the things that are order 2. The things that are order 2, well, there's the 2i theta 1 theta 2 f, but there's also the expansion of this guy. Okay, so the expansion of this guy will give us plus phi dot times whatever there was in tau. On tau there was this minus whatever. Okay, so we'll get minus I phi dot times theta 1 bar plus theta 2 bar. Right? And that ends the terms up to order 2. Now what about the terms of order 3? There's nothing explicitly of order 3 there, but we get terms of order 3 when we Taylor expand psi and psi bar. Okay, so we get plus I square root 2 theta 1, and now we have psi 1 Taylor expanded. So we have a choice of whether to put the theta 1 theta 2 before or after psi. It doesn't matter because it's quadratic. I'll choose to put it before. So this is minus I into theta 1 bar plus theta 2 bar. Okay, now I and minus I cancel, so that's just a plus. As usual, you guys have to police me. Okay, and then of course there's a similar thing from the other side, square root 2 theta 2 theta 1 bar plus theta 2 bar. And this had a psi 1 dot. This has a psi 2 dot. All good so far? Okay. Finally, there's the question of what terms we have a quadratic order in theta. Now, Schumann already pointed out in the last class that you never get anything at quadratic order from f, because the thing behind f was 2 thetas, and the expansion always has at least 1 theta. Okay? But we do get something at quadratic order from phi. So let's figure out what that is. So clearly this is phi double dot. Now let's look at factors. Taylor expansion is a half at second order, but we're going to get something square. Clearly we don't want theta 1 bar square. So we only want the cross term. The cross term has a 2. Okay, so half and 2 cancel, so no half 2. Okay, then we had a factor of I, and that's getting squared, so that's a minus sign. And then we will get theta 1 bar, theta 2 bar. Good, yes? Correct, correct. So here, Kanu's point is we've been too conservative. We could rub out some terms. Let's do that immediately. So here we can rub this guy out. Theta 2 bar. And here we can rub this guy out. Theta 1 bar. Absolutely right. Thank you. Okay. So let's put these a bit nearer. Psi 1 and this was psi 2. Okay, all good? Now, the next step what we're going to do is take Q1 and act on phi and see what we get. Okay, so suppose we take Q1 and act on phi. Okay, what do we get? Well, first let's take the terms that were del by del theta 1. Okay, so the terms that were del by del theta 1, all we have to do is look at this and act. Okay, so here we get an I square root 2 psi 1. Here we get 2I theta 2 f. Here we get minus I phi dot theta 1 bar plus square root 2 theta 2 bar psi 1. This was psi 1 dot. Thank you. Thank you. These were both dot. Thank you. Psi 1 dot. And from here we get minus theta 1 bar, theta 2 bar, phi double dot. Okay, so those were all the terms that we got when we just took derivative.
We have psi 2 dot terms.
Psi 2 dot, I missed that, thank you. We have, thank you, minus square root 2 theta 2 theta 1 bar psi 2 dot. Thank you. Minus because the order was theta 2 theta 1. Right? Okay, so now we've got these guys. What about the guys that come from theta bar I d by dt? Okay, only terms without a theta bar contribute to these. And then we just take time derivative. Right? So, we have theta 1 bar I phi dot, that's from here, plus, now this will be minus, no, plus square root 2 theta 1 bar psi 1 dot. Check my sign, I got minus and then I flipped theta 1 and theta 1 bar. Okay, then plus square root 2 theta 1 bar psi 2 dot. Okay, plus two theta 1 bar theta 2 f dot. Okay. Then we will get the term from here. Plus or minus phi dot theta 2 theta 1 bar theta 2 bar, and that's double dot now, right, because I take a second time derivative. Okay. Here I have something, here I don't, and here I don't. So the last term is plus square root 2, and now we want an I minus I theta 1 bar theta 2 bar psi 1 double dot. Okay, great. It would have been nice there was colored chalk here, but okay. Now, the next thing we do is just organize this in powers of theta. Okay, so this is plus I square root 2 psi 1, that's good. Linear terms, linear terms are here, here, and here. Already we see something in the linear order. This guy cancels this guy. Okay, so plus 2I theta 2 f. Okay, now quadratic terms. Okay, let's see. Theta 2 plus square root 2 theta 2 bar psi 1 dot. And here, did I really get a theta 1 bar? I did, right? Yeah, that's fine. Okay, so plus square root 2 theta 1 bar psi 1 dot. Okay, so we've done this term, we've done this term. Oh, yeah, I've done this, I've done this. Okay. Then there was this minus square root 2 theta 2 bar psi 2 dot, and plus square root 2 theta 2 theta 1 bar theta 2 theta 1 bar. So these guys cancel. Okay. Fine. Have I dealt with every term of quadratic order? As far as I can tell. Okay. Then there is the cubic terms, which were this guy, which is minus theta 1 bar theta 2 bar. And this is again minus, but the theta 1 bar and theta 2 are flipped, so they cancel. Okay, well, that leaves us with plus 2 theta 1 bar theta 2 f dot, and then finally minus I square root 2 theta 1 bar theta 2 bar psi 1 double dot. Okay, all good? Fine. So now we are supposed to compare this with the original expansion of phi, and all terms of the same order in theta should be identified with the change of that corresponding field. But now you see we've got a lot of consistency checks of our algebra. We'll soon be able to read off the transformation properties, and then we will have to check whether we've got it right. So let's see. First, let's look at the term which is no theta. So we get delta q1 of phi is equal to I square root 2 psi 1. Right? Then let's look at the term which was theta 1. It's 0. Okay? So we get delta q1 of psi 1 is equal to 0. What about the term that was theta 2? We get, well, here there was 2if, but there it was square root 2. So delta q1 of psi 2 is equal to square root 2f. Right? And finally, delta q1 of f. So for f, we need to look at the terms that were, where were we? There, 2I theta 1 theta 2. So here, 2 theta 1 theta 2, not there, so that's 0. Okay? So this is what we've done by reading off from the lowest order terms. But of course, all the other terms have to automatically work out. Okay? So let's check one or two random sample terms just to see that it's working, and I'll leave the complete checked here. Okay? So for instance, in that expansion, we had a phi, let's take the last guy, the phi double dot theta 1 bar, theta 2 bar. Phi changed like this. So phi double dot changes like this with a double dot. So the term, the prediction is that the term which is theta 1 bar, theta 2 bar in this expression should be equal to I square root 2 psi 1 double dot. Oh, but with a minus sign. Right? Because it came with a minus sign. Because phi double dot there was with a minus. Okay? So is that correct? Let's see, theta 1 bar, theta 2 bar, minus I square root 2 psi 1 double dot. So it's working. It's guaranteed to work, of course. You've not messed up your algebra. You can check all the other components. Okay? They will also work. Okay? You know, so basically you see that we didn't really have to do much of the expansion. Much of what's coming is coming from the lowest terms. And you can set up your calculation to make that clear. But okay, this was not too tough, so we just worked it out. Okay, let's check one or two other things. Q1 should square to 0. Okay? Question, does it square to 0? Okay? So we act with q1 on phi, we get psi 1. But q1 again on psi 1 is 0. So its action on phi squares to 0. What about on psi 1? Well, that's 0. What about on psi 2? Okay? Well, q1 on psi 2 gives 2f, but q1 on f is 0. So q1 is certainly, and q1 on f was 0, so there was no issue there. Okay. Let us do one more of these calculations. The rest I'll leave as exercises. Okay. The last calculation I wanted to do was to do the same thing for Q acting on, what we need is 4 different things. We need Q acting on phi, Q acting on phi bar, Q bar acting on phi, and Q bar acting on phi bar. Now, of course, Q acting on phi and Q bar acting on phi bar are very similar to each other. Q acting on phi bar and Q bar acting on phi are very similar to each other. So really, we need to do one more calculation and keep our wits about us. So let's do that one more calculation. Okay, since we've expanded phi so nicely, let's work out Q1 bar. Let's work out Q1 bar. And actually, sorry, we needed to do these calculations for Q1 and Q2. Now, Q1 and Q2, you'll get almost identical results. But there's one place here in this expansion where we've broken the symmetry. Can somebody tell me where? Well, in the original expansion, let us check. So, sorry. In that expansion up there. Oh, I've got fiber. In that expansion, the first expansion on the board, there's one place where we've broken the symmetry. The 1-2 symmetry. Exactly. Theta 1, theta 2 is minus of theta 2, theta 1. So when we do the calculation with 2, yes, the rule will be to flip 1 with 2, but also flip f with minus f. So we can get the results for 2 free, but remembering also to flip f with minus f. Okay, so for instance, let's just immediately here write down was let's write down the rule for 2. Okay, so this is delta q2 phi is equal to I square root 2 psi 2. Delta q2 psi 2 is equal to 0. Delta q2 psi 1 is equal to minus square root 2 f. And delta q2, well, minus f, but that doesn't matter since it's 0. Okay. So 2 out of the 8 properties we want, 2 out of the 8 things we want are up here. Let's work out another 2 and then figure out the other ones. Okay. Okay, fine. So let's work out now what we would have got. It would be nice to keep phi's expansion up there. So let's keep that up here and move here. So phi is here. Let's work out q1 bar on phi. Okay. Now we'll again try to be a little clever, just to save a little time. Okay? How can we be clever here? Well, we can be clever in the following way. You see, q1 bar has phi was a function of theta 1, theta 2 and tau. q1 bar acting on theta 1 is 0 because it's del by del theta 1 bar. There's no del by del theta 1. Okay? q1 bar acting on theta 2 is 0. So the only place where q1 bar acts is tau. Okay? But you remember that tau was annihilated by d1 bar. That's how we determined tau. Okay? So we want q1 bar of phi. This q1 bar acts only on the tau. But remember that, okay, so q1 bar was del by del theta 1 bar plus I del by del t. But we know that d1 bar on phi is 0. d1 bar on tau is 0. Theta 1. Thank you. Thank you. So, but we know that del by del theta 1 bar minus I del theta 1 del by del t acting on phi or on tau is equal to 0. Okay? So that tells us that we could replace this by twice of one of these two. Let's choose twice of this guy. Okay? So q1 bar acting on phi is the same as 2I theta 1 del by del t acting on phi. Right, because I add and subtract, and what is left is a d bar. Okay, so that speeds the calculation up a bit. Instead of taking 2 terms and getting lots of cancellations, that's a lot of what happened in the earlier thing when we got cancellations. Okay, so so let's now keeping this in mind, let's evaluate 2I theta 1 del by del t on phi. Okay, phi is out there in front of us. Phi is out there in front of us, so we'll evaluate the first few terms. Okay, the first term is 2I theta 1 phi dot. Now this will give us 0 because there's a theta 1. The next guy will give us minus 2 square root 2 theta 1 theta 2 psi 2 dot. Right? This will give us 0, and let me leave going to higher orders as an exercise for you, because higher orders will only give us the consistency checks. Right? Because once we have it up to second order, we already find the answer, and then there is consistency checks that we're doing it right. Okay, so let me just trust our magnificent algebraic skills. We're not making mistakes, so we will do it just to these two orders. Okay, so now what do we comparing this with q bar on phi? What do we see? We see del q bar on phi is 0 because there's no term without a theta. Del q, this is q1 bar. Q1 bar on now let's see, del q1 bar of, I'm sorry, anyway we can remember the expansion up to this order, right? So the theta 1 term was the psi 1. So del q1 bar on psi 1 is equal, there was an I on both sides, there was a square root 2 phi dot. Del q1 bar on psi 2 is 0 because there's no term that's just linear in theta 2 here. And this guy was the f term. Now f came with an I, with a 2I theta 1 theta 2. So this is what's left is an additional square root 2I. Right. So del q1 bar f is equal to square root 2I psi 2 dot. Do you agree? Okay, and then we can very, basically free read off always the same rule, right? Flip 1 and 2 and flip f to minus f. So del q2 bar phi is equal to 0, del q2 bar psi 2 is equal to square root 2 phi dot. Del q2 bar psi 1 is equal to 0, del q2 bar f is equal to minus square root 2I psi 1 dot. Okay, now we're ready for another check. The second check is that q1 bar plus q1 bar q1 should be twice h. H is I d by dt. I don't know if you're like me, I can never remember whether Schrodinger equation has an I d by dt or a minus I d. Somehow, it's e to the power minus I h t. It's I d by dt. Okay. Right, because I d by dt is equal to h psi. Therefore, you take the minus I to the other side. That's why you get e to the power minus I h t. So the I d by dt is the Hamiltonian. Right. Okay, excellent. So now let's check. Let's check first action on phi. Q1 bar is 0 because Q1 bar acting on phi is 0. Okay. What about Q1 bar Q1? Okay. So we first act with Q1. So we get 2i square root 2 psi 1. And then we have to act on psi 1 with a Q1 bar. This is psi 1. We act with a Q1 bar. We get square root 2 phi dot. Square root 2 times square root 2 is 2. We got 2 times I phi dot. So 2i d by dt. Okay. Let's quickly check the others as well. Let's look at psi 1. Q1 bar Q1 is 0 because Q1 annihilates psi 1. So what remains is first acting with the Q1 bar. So Q1 bar gives square root 2 phi dot, and then Q1 on phi is this same algebra. These two are sort of dual to each other. Okay, all good? What about psi 2? Very similar. Q1 on psi 2 is, so Q1 bar on psi 2 is 0. So we only have to look at Q1 bar Q1. I mean, first act with Q1 bar. Sorry. First act with Q1, so we get square root 2f. And then act on square root 2f with Q1 bar, which is square root 2i psi 2. So you get I d by dt. 2i d by dt. 2i d by dt. And similarly, when we act on f, this guy, and then Q1 on psi 2, once again it works. These two are sort of dual to each other. Okay? So we've checked that the transformation rules that we have computed obey the supersymmetry algebra, at least when acting on phi. Okay? Now, the last thing that we need to be complete, absolutely complete, okay, the last thing that we need to be absolutely complete is to find the supersymmetry transformation rules acting on phi bar. Okay? Now, how do we go about doing that? Well, of course, we could do the calculation again, but that would be silly. Okay? Let us remember that the expansion of phi bar, that in the expansion of phi bar, we've got two things that are different. Well, first, explicit thetas are replaced by explicit theta bars. Well, three things. First, explicit thetas are replaced by explicit theta bars. Second, tau is replaced by tau star. But let me remind you what tau and tau star were. Tau was equal to t minus I theta 1 bar plus theta 2 bar. Tau star, therefore, was equal to t plus I, same thing, but you can write it more illuminatingly as t minus I theta 1 bar theta 1 plus theta 2 bar theta 2. So you see, tau star is just tau, but interchanging the roles of bar and unbar. Okay? So you see, the expansion for phi star has exactly the same is exactly the same as the expansion for phi, with the one change that every theta is replaced by a theta bar, and every field is complex conjugated.
And not the i's.
What? No, the expansion for phi star had the same i's because of the anti-commutations. Right? Unless in F was there, oh, maybe in F was. Yeah. Let's check. If we took I theta 1 theta 2 F, yeah, even here, as long as we flipped back the 1 and 2, Yeah. In all of them, the expansion for phi bar had the same eyes as the expansion for phi. Shall I? Let's right?
You flip 1 and 2.
Flip 1 and 2 and complex conjugate the fields. The fields as a function not of tau but as a function of time. Okay? So every time you see a field you put a star.
Just complex conjugate.
Just complex conjugation and flip theta and theta bar. Right? So now because we've got that nice rule, let us write out the supersymmetry transformation properties for all fields under for the complex conjugate fields. You may think this is bad algebra, but we can do it on the board, right? Anyone who's seen a supergravity action, they know what bad algebra is. Okay, this is okay because it's such a tame version of things that will occur repeatedly. My idea was once in your life you see it done with every sign. Okay, and the rest of the time you take it from papers and then you write a paper and then you realize the original paper had a minus I mistake in the third term. And your paper is wrong. Okay. 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 Fine. But anyway, that's what we'll do. At some point, we'll stop doing this dirty algebra. We will accept what people have done in books and papers, but not at this stage. Just so that you don't feel I'm sweeping things under the carpet. Okay, fine. Okay, so now what was our rule? Our rule was we can now get, so delta theta bar, so delta q1 bar, remember we had to flip theta and theta bar, that is the same as flipping q and q bar. Okay, so delta q bar on phi star had exactly the same rule as delta q on phi. Right, because our rule was flip theta and theta bar and flip field and its complex conjugate. So flipping theta and theta bar takes q1 to q1 bar, and then we should take complex conjugate. So we get delta q1 bar on phi star is equal to I square root 2. We're not touching the i's, just the fields are complex conjugated. That was our rule. Right?
This is psi 1 bar.
Psi 1 bar, psi 1 bar. Psi 1 bar. If you want, we can call this also phi bar to be considered.
You just put bar in all the formulas.
If you put the bar also in the q's. Yeah, just put bars in all the formulas. Fine, exactly. So maybe we don't even need to write it down. Okay, so let's just write down the rule. Including okay, so we've got these supersymmetry transformation properties in our hands, and the last thing I want to check about them, you see, now since we've got this very simple rule, all the consistency checks that we did for q1 squaring to 0, q1 bar being Hamiltonian, guaranteed to work also on phi bar. It will be the same algebra, so no point doing it again. Okay, so algebra is working out very nicely with these rules. It's also clear, nice complex conjugation happening here, right? Okay, the last thing we should check to make sure that our algebra is complete is that it's consistent with the algebra we have is consistent with eliminating the consistent with eliminating the auxiliary field. Okay, let's check that. Schumann had told me what? F star is equal to minus I w prime phi, and F is equal to I w prime star phi. Here in this, yes, everywhere you should. Bar includes F bar. Yes. Schumann, I've already managed to forget it. Can you read it out again, please? F was equal to what? Star. Yeah, bar. W prime bar, which means W prime bar phi bar. Okay. And F was equal to I. You sure this relative I?
Previous one was F. The next one was F bar is equal to I times W prime I.
Are you sure the relative I was here? Huh?
The opposite sign. Sorry, F star is minus sign and F is plus.
F star is minus sign and F is plus sign. Yeah, this minus, relative minus sign. Anyway, will it create trouble? Let's see. Okay, let's see. So, let's see. So, now we want to know if we plug this guy into here. Okay, if we plug this guy into here, now we seem to have two different transformation rules. And it appears that we have two different transformation rules, one from the direct transformation rule of F, and the second from whatever the constitutive relation for what F was. Okay, we want to know whether that is correct up to equations of motion. Okay, so let's check that once. Let's check this guy. Okay, if I plug F in for, let's say, first let's check the 0. The guy that was delta Q1F. So F was now a function only of phi bar. So delta Q1, okay, sorry. So I want to check whether it's correct that we had delta Q. So these are the relations I'm going to check. Delta Q1 on F is supposed to be 0, but F was this function of phi bar. So F was I W bar prime of phi bar. So we want to know whether it's true that delta Q1 on this quantity is actually equal to 0. But how do we compute on phi bar? Okay, how do we compute on phi bar? Well, just we bar all the quantities. So that's the same. That would only be true if it were true that delta Q1 bar on I W prime phi was equal to 0. So that will only be true if delta Q1 bar annihilates phi, but it does. Okay, let's do one non-trivial one and then move on. Okay, let's do the other one. We want, suppose we have delta Q1 bar on F. This has to be equal to 2I psi 2 dot. Okay, this is the claim, but however we know that actually F was equal to I W prime of bar of phi bar. Square root. This had a square root. Thank you. Thank you. So we want to know whether this is working. Fine. Now first we should not get something 0, but q1 bar on phi bar is like q on phi. Which was not 0 because q1 phi was I square root 2 psi 1. Oh, I have written it. Thank you. q1 bar I square root 2 psi 1 bar. Okay, so let's work it out. So this was prime, so now we get minus square root 2 w bar double prime phi bar times psi 1 bar. Right? That's what we're supposed to get. On the other hand, we want to know whether this is equal to square root 2I psi 2 dot. Okay? And for this, we're going to use the equation of motion. So let's go back to the Lagrangian, which maybe is easier to get this way around. Here's our Lagrangian. Okay, so how could this possibly work? It could possibly work if we took the equation of motion with so psi 2 dot comes here, psi 2 bar equation of motion. So the psi 2 bar equation of motion tells us, now let's take variation on the left, so we keep our signs straight. So I psi 2 dot, but where else does psi 2 bar appear? Well, it appears here in the plus cc. Plus w dub prime bar yeah, psi 2 bar will be on the left, exactly. Psi 1 is equal to 0. Psi 1 bar, thank you. And that's exactly this equation. Square root 2's have cancelled here. Oh, is it exactly? Is the sign right? Yeah, it's exactly right. Right. Okay. So all our algebra is beautiful, it's self-consistent, gives you the right thing. Now, what I had wanted to do in this class, but it's taking too much time. So, okay. Now that we have, okay. Now, Shuman will really this week send an assignment. Okay. And this problem I'll just leave for you as an assignment. Okay. The problem is now this. Now we have all the supersymmetry transformation properties bang in front of our eyes, right? Now the question for you is to turn this problem into, turn the supersymmetry operators into Hamiltonian operators. Okay? So remember, what is our Hilbert space? Our Hilbert space is made up of what? This is just quantum mechanics. What is our Hilbert space? Well, our Hilbert space is generated by phi and pi phi, phi bar and pi phi bar, which is another complicated way of saying that it's square integrable wave functions of a complex variable. Complex variable being phi. Okay, functions of two variables, phi and phi bar, square integrable, and then pi is taking derivatives. Right? Pi is minus I del by del phi, minus I by del phi bar. Okay, these, but also sigma 1 plus, sigma 1 minus, let's minus, which remember secretly was psi 1, sigma 1 plus, which secretly was psi 2, psi 1 bar. Okay, sigma 2 minus, which secretly was psi 2, and sigma 2 plus, which secretly was psi 2 bar. Okay, So these operators generate a Hilbert space. So what is the Hilbert space? Well, the Hilbert space is 4 component square integrable wave functions of 2 real or 1 complex variable and its complex conjugate. Those are our wave functions. That's our Hilbert space. Okay. Now on this Hilbert space, the exercise is the following: x1. Okay. Write out the operators. Operators that generate the supersymmetry algebra, that implement supersymmetry. This is exercise 1. Okay. Exercise 2 is to work out, check the SUSY algebra as obeyed. A part of this exercise is to determine the Hamiltonian. Because how do you check the supersymmetry algebra is obeyed unless you know what the Hamiltonian is? But compared to the Hamiltonian is obeyed with the same Hamiltonian you get by canonical quantization out of a Lagrangian. Okay, let's write that down. What was a Hamiltonian? So this was a Lagrangian. Okay, so this was a Lagrangian. Well, clearly the Hamiltonian here is going to be momentum squared plus momentum squared, or the complex momentum squared if you want, p phi bar. Okay, from this part you get 0 because these are first order in time, and from this part you get plus mod w prime squared, and from here you get plus whatever this guy is, replacing psi 1 with sigma 1 minus and psi 2 with sigma 2 minus, and so on. Is this clear? So the Hamiltonian from here is transparent. You just read it off. You should get that the supersymmetry algebra is implemented with that Hamiltonian. Okay? And the third and most interesting part of the exercise is to explicitly work out the exact ground states of this problem. You know, we've got plenty of equations to help us work out the ground states, because ground states obey the equations are annihilated by both q1 and q1 bar, but also by q2 and q2 bar. So the ground states have to satisfy 4 first order differential equations. What?
Also d bar.
D bar. Now d bar was a quantity that was for the expansion of the superfield. This is a physical thing we're talking about. The Hamiltonian has to happen. The principle is that the Hamiltonian has to be annihilated, but you're probably right in the end, is that if you wrote down the other supersymmetries, they will also probably annihilate it. That's probably right. I would have to think about that to make sure. But we don't need that. Okay? We're really dealing with the supersymmetry. D bar, in my mind, is just a trick to be able to build a superfield representation. Q is the real operator. Okay, fine. Okay, so you get plenty of equations. Actually, something I didn't stress last time when we were doing the one-dimensional problem, the one particle problem, is if you remember, we found the wave function by letting q annihilate it. You could also have let q bar annihilate it, and you got the same equation. If you remember, there was a 1 and 2 interchange, and then there was an I interchange. And so because of that, you would still get the same sigma 3. You can check that. Okay? So in the same way here, though it looks like you've got plenty of equations, you will have in the end actually only 2 equations. The other 2 will be dependent. And these 2 equations will tell you the dependence of the wave function on phi and on phi bar. Okay? So the exercise is to work this out. Work out the ground states of the problem.
You said that first find the operators and then check the
Yes.
operators itself will be formed by the algebra, right?
The way I would find the operators.
Commutator of Q with something.
No, that's not how I would find the operators. The way I would find the operators is to find the operator which, acting on the states, the operators in Hilbert space, produce the right supersymmetry transformation properties. Let me give you an example. You can find the commutator, but you want to make sure not just that you've got the right commutator, you've got the right operator. Right? How are you going to find? Well, for instance, you could.
For D and D star in the case of sigma model by.
You're saying once you know what the operators are, you find the commutator to find the Hamiltonian. That I agree with. But the first thing you need to know is what the Q and Q bar are.
No, but we know the action of Q on X, Q on psi.
Okay, so then maybe we're saying the same thing. I'm saying you find Q by finding because you know the action of Q on everything, those boxes. That's what you meant? This is correct. You find Q by that. Then you find the Hamiltonian by using the commutation relations. And you check that Hamiltonian is the same thing that you got out of canonical commutation relations. That's what I was suggesting. Is this clear? This part of the exercise will just help you get familiar with some machinery. Most interesting part is what are the ground states. Actually, I haven't worked it out myself, but I'm sure it's possible to work out, and you guys will work it out. Okay? Wonderful. So I think that if you're okay with this, and if you guys, I will actually do the assignment. If you want, I should spend the time working it out, right? So we should see one complex model worked out completely. But I'm assuming all you guys are very serious people. You're going to do your assignments, even though this is not a formal course. Okay? Fine. So just in the interest of speeding things up a bit, I'll leave this to you to work out. It would have taken the next hour if we tried it ourselves, I think. So let's move on. Okay? Great. So we will declare this one complex dimensional problem done, and I will once again display the supersymmetry relations that we are so proud of. Actually, maybe that is better. So that the camera captures it, and then we move on to the problem of many complex coordinates. Okay, great. So now what we're going to move on to study, which is really perhaps the main reason for introducing this extra supersymmetry. Well, there were 2 reasons I wanted to introduce this 4 supercharge problem in this class. The first is so that you get comfortable with this algebra. Actually, that's one of the main reasons. Okay, it's the simplest context in which you see this, in which this algebra is performed, that one repeatedly needs to do to produce supersymmetric theories. It's simple, there's nothing to it, but you have to say it once. That's one reason. The second reason was for the physics, and the physics is that of scalar manifolds. Okay, and that's where we're going now. Okay. So the question that I'm going to ask is the following. The question I'm going to ask is the following, is this. Suppose we had not one chiral superfield, phi I, but many chiral superfields. Sorry, not one chiral superfield phi, but many chiral superfields phi I. Okay, now we know how to write down Lagrangians. So the Lagrangian we are going to study, or the action we are going to study, is minus 1 by 4 f of phi I and phi I bar. d4 theta, by d4 theta we mean the coefficient of theta 1, theta 2, theta 1 bar, theta 2 bar. This is what we mean by d4. Okay? Plus half w of phi I plus cc. And by this w of phi I, what we mean is the coefficient of theta 1, theta 2. That integral. Suppose this was our supersymmetric Lagrangian. The main innovation now is two things. First, we've got more fields, and second, we've allowed for a more imaginative kinetic term. Right? Last time our kinetic term was just phi bar phi. Now we are allowing for something a little more imaginative. Any function of the superfields phi and phi bar. Now, what we are going to try to do is to understand this theory. Okay? So our goal is to understand this theory. But before we start, getting into the indices and so on, well, one thing about this theory that you can say immediately, and that is this. Look, f, as long as it's a function of phi and phi bar, gives you something non-zero. But had f been just a function of phi or just a function of phi bar, we would have got 0. As we argued last class, that you cannot integrate, you cannot perform an integral over only chiral superfields over 4 supercharges, over 4 thetas. Okay? So this f here, what we've learned is that this f, if I take this f and I make the transformation, f goes to f plus b of phi plus cc then I end up with the same Lagrangian. So the data of this on the kinetic term is functions of phi and phi bar modulo shifts by chiral functions plus complex conjugates. Now, some of you people here are experts in mathematics, and if you are familiar with the mathematics of manifolds, this will immediately remind you of something. It immediately reminds you of Kähler manifolds, where the metric is defined by a Kähler potential, which is a function of z and z bar, but the metric depends not on the scalar potential itself, but is left invariant up to holomorphic shifts. F of Kähler potential, the Kähler potential plus holomorphic plus complex conjugate leaves the metric unchanged. Okay, this is already an indication that what we are going to land up with here is that this is going to turn out to be the Kähler potential of a Kähler manifold in a kinetic term. Okay, so now we want to see this. We want to see this working properly.
Does it have to be complex conjugate of theta, or can it be another function?
Well, you want it to be real, right? You want your Lagrangian to be a real thing. Yeah. So just for the algebra, for getting 0, it could have been anything, but I said complex conjugate because I real Lagrangian. Okay. So now we want to see this working in more detail. Okay, and So we want to open out d4 theta up to total derivatives. F of phi 1, phi I bar. Okay? So this exercise is very similar to the exercise we did last class of opening out just phi bar with some small differences.
So in the previous case we had phi bar occurring together as a product.
Yes.
So here phi I can pair with other.
It could be an arbitrary function. You know, it's not even, there's not even a question of pairing. It's just some function of phi I and phi I bar. General function. But as we've seen, any part of it that is pure, it should be real. And any part of it that is purely holomorphic will just give 0.
There should be some
anti-holomorphic, some anti-holomorphic piece. Right. Okay. So let's see. So our field expansion is out here. Each phi is expanded in superfields like this, and phi bar has the identical expansion, replacing all phi bar had the identical expansion, replacing all thetas with theta bars and fields with complex conjugates. Okay. So we have everything that we need. We just look here. Okay. So right. So let's move. We want to get the term that has 4 thetas in this. So of course what we want to do is Taylor expand this in thetas. Okay. Thetas come, so let's just do the Taylor. Let's schematically start doing the Taylor expansion. So these are all superfields, phi I and phi I bar. Okay. Okay. So let's see. So suppose we take the first term in this thing is clearly going to be just f phi I and phi I bar. Okay. Plus there will be del f by del phi I times the small change in phi I. So that's everything apart from phi in this expansion here, and so on, and we can go up to 4th order to produce all the terms that we need. Okay. Let's first, clearly at 0th order we get no terms that we need because we need 2 thetas and 2 theta bars. Okay. What about at 1st order? Okay. What about at 1st order? What do we find at 1st order? Well, at 1st order we have theta 1 bar, theta 2 bar, and we have a phi double dot. Okay. So this gives us a phi I double dot. Now notice that the 1-2 order, our rule was theta 1 bar, theta 2 bar. That had a different order. That takes care of the minus sign. Okay. And theta 1, theta 2, theta 1 bar. Yeah. And then we will get the same plus del f by, now I shouldn't really be using this f, right, because that will confuse us with the, let's call it something else. It's what people normally call it, unfortunately. Let's call it p. Okay, let's call it p, just for fun. Okay, plus del phi I bar, phi I bar double dot. Okay, this is one term. So this is not really there. This I just wrote for fun. This we're only keeping the terms that are contributing after we've done the theta integrals. Okay, great. Next, the terms at second order. Okay, so there are two kinds of second order terms we could get, or three kinds. There's second order, which is del p by del phi I, del p by del phi j, del p by del phi I, phi j bar, and then phi I bar, phi j bar. All three can contribute. Okay, so let's take the first kind, where we've got two phi's. Okay, now when we've got two phi's, we want to find terms here that can come together. Okay, we want to find terms here that can come together to make up 4 phi's, for all 4 thetas. Okay. Now, let's see what could do that. We could have phi dot can do, and nothing else, right? F was 2 thetas. So we want theta, theta, theta bar, theta bar. Right? That won't do it. Okay? No other combination of terms will do it, right? Because we want to get 2 theta bars, and the only way we can get 2 theta bars without having extra thetas is from here. Right? Fine. So we get plus d2p by d phi I d phi j. Then each of these would come with minus I, so that would give you a minus sign. And then we would get half from the Taylor expansion, factor of 2 from this guy, theta 1 bar, theta 2 bar, and therefore minus sign, and so plus. And of course multiplying phi I dot, phi j dot. Notice that the terms we've got so far are very similar to these terms. Okay? And in fact can be converted to this term by an integration by parts. Right? Because if I integrate one of these time derivatives by parts, okay? But are we getting the sign so it cancels? Okay, we just calculate them all. I hope the signs are correct. We integrate this by parts. We will get a derivative here, so del by second j derivative and phi j dot. Looks to me like these two terms, if we've got the signs right, are.
This phi I double dot has a minus sign.
Which one?
Phi
This one?
first term.
Yeah, let's check that carefully.
Capital phi has a minus phi double dot. Theta 1 bar, theta 2,
We want theta 1, theta 2, theta 1 bar, theta 2 bar. It's a plus sign, and we did it right here as well. Okay, let's just keep going. Because here we got this guy square, I square, so that's minus, but then again we got the sign theta 1 bar, theta 2 bar. Again the same thing. Okay, let's just keep going. Might be other sources. I'm surprised though. I'm surprised that at this stage. Anyway, let's see. Let's keep going. What? Well, I expected an answer proportional to this, but not 0. Yeah. I mean, for the scalars, this is what you expect. Right? the metric is second derivative of this scalar potential.
But it is like
But we will only get a complex metric. This is 0. This is 0. Thank you. This is 0 because we should only get z bar. Thank you. Very good. Very good. Very good. Thank you. Thank you, everyone. And therefore, these two terms, now that we know it's the right answer, we happily kill them. There was a second term like this for the bias. So we kill them. So okay. So far we've got nothing. But we still have what we would have got from 1 phi and 1 phi bar. Okay. So these now I'm just throwing away. This cancels this, plus CC cancels this. And now we need to keep what we get from 1 phi and 1 phi bar. Okay. Now that is more difficult. So we want to keep all the quadratic terms, sorry, all the terms in which we can match this expansion with the barred expansion and get a theta 1 bar, theta 2 bar. Okay. Yes. So let's see. We're going to get plenty of contributions, but let's first take the contributions that involve only phi. Okay. So that is this guy, and that is very similar to what we did before, right? That is very similar to what we did before, because we've got one expansion with respect to phi, one with respect to phi bar. We don't have a half. Okay, so this is del p by del phi I del phi bar j. Now we will get this minus I square, and
there, when we do integration by parts, there is one more term.
phi I. Let me write this down if you don't mind. Phi I dot phi j bar dot, and then with a plus. I'm getting this from this. Sorry.
In integration by parts, there will be del 2p by del phi I, phi bar j, and phi I dot phi j, which will I think add to this, right? When we do total derivative.
Thank you. Very good point. Here, this was also a function of excellent, and thank you. So, thank you, Chintan. So, Chintan's point was that when we took the total derivative, we went that side. We also get minus del p by del phi I del phi bar j phi I phi j bar dot. What? Phi I dot, and then we would get a very similar term, the same term from here. Okay, so minus 2. So Chintan's point is that this was our final contribution from those upper terms. Thank you. Okay, and here we are getting this. This you claim as minus, or this one? This one. Lower one? Let me check that. So we expanded, we get a minus I and a minus I, minus sign, and then one sign flipping thetas.
No, for the derivative with respect to phi, the order is theta 1 theta bar, and for the phi bar it will be theta 2 bar.
Ah, you're right. In phi bar it was theta 1 bar theta 1. And therefore, you say that what we get is like theta 1 bar, theta 2 bar, theta 2. And then, therefore, we get a plus sign. And so we get a plus sign. Right, good. So we get a plus sign here, and so overall, sorry, thank you. So we get overall a minus sign. So we get a factor of 3. I hope we're doing this right. Just 1 minute. Oh, but we get an extra 2 as well, right? Because there are 2 of these terms when we square it. That makes more sense. Because then we get the factor of 4, and then the minus 4, minus 1/4 makes it 1. Yeah. Thank you. Thank you. So far what have we deduced? I'm sorry for being so unsystematic here, and thank you for all your invaluable help. So far what we've deduced so far is we've got minus 4 dp by d phi I d phi bar j phi I dot phi j dot in this expansion. Okay, but we've got miles to go. Okay, we've got miles to go because we have all these other terms to keep track of. Okay, now let's see. Now let's keep track of terms that involve psi. Okay, so let's first get the term that has 2 psis. Acha, which are these? No, that we've already taken care of. That was this first term here. That was the term in the first order expansion. Right? Now when we're taking second order expansion, we have to take 2 terms, both of which have some thetas in it. Okay, great. Yeah, I wouldn't have liked it if there were more terms because 4 is a nice number. Okay, fine. Let's look at the terms that involve 2 psis. Well, such terms exist because we could have a psi from here and a psi from here. But of course, we want it to come with the bar. So, what do we have? So, right. So we have, when we make this guy a bar, it has exactly the right theta structure to contribute with this guy. Okay, and so we will get minus I. Okay. There was I, there was 2 square root 2's, so there was I plus 2I. We will get then 1 term here, and then we'll take the other term as well. So 1 term here is theta 1 bar, theta 2 bar, theta 2. Okay, so this is plus sign. Okay, and then that was psi 1 bar dot.
But there is a 3. Change the 3, it will have minus.
What?
You change the 3 thetas to the other side of psi, right? To combine with
Yeah, that is a danger. That is a danger. Yes, that is a danger. Let's see. So we had a theta. Okay, so you're correct. Let's work it out carefully. Let me write it out. So it's plus I square root 2 theta 1 psi 1 and times square root 2 theta 1 bar theta 2 theta theta 2 bar theta 2. Okay. Psi 1 bar. Psi 1 bar dot. Okay. And your point is I have to take this guy through here. 3 of them. So that's a minus sign. And I have to take theta 2 through here. So no sign. So I get minus I. Minus I, yeah? Oh. Okay, fine, right. So you get, so this whole thing here was minus I, minus 2I, psi 1 bar dot. Psi I, psi j, yes. Psi. No, okay. Now we have to be a bit careful because we have 1 and ij, and this is d 2p by d phi I d phi bar j. Good? And there will be another term, I know. Well, it'll basically, one sec. Now first, let's take this term and put the phi bar j, or let's integrate by parts, because we like to write our terms with a with time derivative on not bar, the guy in front. Okay, that's good because we know that the correct kinetic term is a minus sign. So we've got the correct kinetic term here, and we've got the correct kinetic term, and then there's going to be a second term which will be basically identical, right? Because it's only a question of which. What else could you write? Right? Because whether the time derivative is on this guy or on this guy makes no difference, right? So I think this is just going to be plus 4 5. We could work it out if you want, but it's sort of clear, right? Okay, so we've already found the two most important terms in the Lagrangian. Okay, we've already found the two most important terms in the Lagrangian. Okay, which are what's going to play the role of the metric times the kinetic term, and what's going to play the role of what? Same metric, yes. Same metric times kinetic term for the fermions. Okay? And this 1, 1 and 2, 2 is like going along for the ride. Whatever happens with 1 also happens with 2. So there's a summation there. Okay, yeah. Yes?
In that, the other phi double dot, I can multiply normal phi j and that can give a contribution.
Yes, that was the first contribution we took.
That was only one phi double dot. I'm saying phi double dot I, phi j, and that.
Phi double dot I with what?
The normal phi double.
That was the first contribution we took. Because you see, the Taylor expansion was Taylor expansion in all of this. It's this plus small. So you're not allowed to take from here. Do you understand? What we're doing is expanding f, or we call it p, as phi I plus delta phi I. Anything with a theta is delta phi I. Okay? So when we expanded at first order, that was the term which was this multiplying f prime of phi I. That's the term you're talking about. Okay? That's not different. We've already dealt with that. Okay. Now, last lastly, we'll keep track of the terms. Involving f. Yes.
How are you interpreting the second term as kinetic term because there is only one time derivative there?
That's how fermions are, right? Fermions are first order in time. This is the standard. If you take the -1/4, it's the standard kinetic term we get for fermions. Okay. Now there are going to be other terms. I'll just work out one last one, the one involving f, and then we will I'll give you the answer. I'll give you the answer for the rest, basically by guesswork. Okay. But before that, let's work out the terms involving the f. Okay. So the terms involving the f are what? Well, in this expansion for phi, there was basically one term with f. So a term with f here would have to meet something else with two thetas, both bars, and that will basically be another f. Okay. And so we are going to have clearly it won't come in the term. Well, we've already done the term with two phis. It's phi bar. Okay. So we're going to get plus del p by del phi I del phi bar j. Now this guy had theta 1, theta 2, theta 1 bar, theta 2 bar, minus sign, so I'm getting plus 4. Fi fj bar. Y plus 4. I'm getting minus because we are squaring. Oh, no, but you're going to tell me I got the order wrong. So let me check. Theta 1, theta 2, theta 1 bar, theta 2 bar. Then that gives us a minus sign. No, this is fine. This is just the order. Right. It's the order we want. Then we got minus squared. So I get a minus. Huh? You're probably right. Just a minute. What was the reason I thought it was plus? Just a minute. Theta 1, theta 2, theta 1 bar, theta 2 bar. That's the order. Yeah, a minus. Correct. Minus. Thank you. Okay. Now, we're going to get other terms as well. But many of the terms we can guess from here. One set of terms that one can guess comes from the fact that this del pi, del phi I, j, del phi I, del phi, j, phi bar j is playing the role of the metric. So psi I dot should come as a covariant derivative. Okay. So psi I dot should come as a covariant derivative with the gammas built out of this metric. Okay. So now when we write down minus 1/4, integral d4 theta p, this will be what? It will be del p by del phi I del phi bar j, phi I dot phi j bar. Okay. Well, let's not write integral here. This plus minus psi I dot, and this is A. A is summed over. That's 1, 2. I'll leave in 4 minutes. I'm sorry for. Yeah. Yes. Yes. In 4 minutes we leave. Okay. Fine. So this was this. Now we will make this d by dt. Psi a j bar del p by del phi I del phi bar j. And that's it, where this is the usual thing, right? This is the time derivative plus gamma times times psi times del phi I by del t. What we had last time, right? Just that the gamma this time is built out of a slightly simpler metric, one which is del p by del phi I del phi I bar. Okay. These are the terms we've got so far, and then of course there's the f's. Sorry. Plus del 2p by del phi I del phi bar j fi fj bar. Okay. We've not got all the terms. What we've not got is the analog of the curvature term from last time. Okay. That term I will we will try to sort of guess, or next time we get that term next time, and then we'll proceed. Okay. I'd like to finish at least the superpotential, but we won't do it this time. Yeah. Okay. So next time we work out the superpotential term. We can sort of guess that, right? Okay. Let's do it next time. Let's do it next time. Okay, we can guess it by, we know what it is in one-dimensional case. We know it has to come built out of the metric. So there's a what else can it be kind of thing. So I'll leave you to essay a guess for what the superpotential term should be. Well, it's pretty clear. And then there's the curvature term, and then we've worked out our Lagrangian. Okay, and we will continue next time to understand this model a little more, to understand what it has to do with Kähler geometry. Okay, it would be really nice if you guys could work out the assignment, today's assignment, before next class. Okay, that would help us a lot. I will start next class by outlining the answer to this time's assignment, because we'll need it when we move on to trying to understand the Kähler geometry. Okay, we'll need parts of it. Okay, thank you.